Hello everyone, welcome back to another lecture. It is your favorite IA, Mia, and I am here to talk to you today about plotting and fitting functions in Python. So today we're going to talk about discretization of functions, how to plot functions, subplots, and data fitting. Why do these things matter? Data fitting is really important for scientific discovery. When you have some data, it is really hard to tell general trends, especially when you have a lot of points or a lot of things in a space. So we use data fitting to try and show easily the trends that we see in our data. I use it all the time in my work, in my research, and I'm sure you guys will as well in other classes, in our class, and also elsewhere in the world. So why do we discretize functions, really? Computers are good at doing a lot of things. The one thing they're not really good at, though, is continuous infinite functions. This is because computers inherently work with numerical data that is discrete. So discretizing functions are necessary for digital computers. They have to break it down into smaller components. Like, for example, let's say you were trying to, in Python, code a simple function y equals x. How could you think to set or create this kind of equation in Python without setting any limits? How would you define how many x values it goes through? And then even if you say, okay, we're going to do x equals 1 and x equals 2, how will it know how many steps in between those two numbers it needs to take for it to be infinitesimally continuous? You see, there's a lot of things there, and obviously there have been a lot of work to try and fix these problems, but the best way, at least for now, is discretizing functions or breaking up these large continuous chunks into discrete, smaller pieces. And these approximating functions are really great because they allow you to save memory space and time. Your simulations will run faster, your calculations will run faster. Then, this still also allows for highly accurate calculations, especially where we are today, even though there will always be some percentage of error. As long as you're keeping track and being careful, you're able to get really good numbers. So you might be wondering, how do we actually do this? Taylor series is one way of discretizing functions. You might have already learned in other classes. We're going to kind of go over that and use it here in Python to show how we actually do this. So, in case you forgot or you haven't learned yet, what is Taylor series? A Taylor series is representing a function as an infinite sum of polynomial terms based on their derivatives. So we're going to approximate a Taylor series by using some amount of terms n, and this will change throughout this example. So, for example, we're going to look at y is equal to cosine of x. It's a very common Taylor series, very famously known as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. We can clearly see this pattern of alternating minus and plus signs, and then also where all the numbers are even. This is purposeful, of course. This is the Taylor series that represents cosine. And we're going to kind of talk about how we get there in Google Colab. So this is something I wrote up really quick to kind of go through this example. First thing we do here is import the modules that we need. These statements right here are not necessarily necessary. I like to use them just because they make my code a little bit shorter, but again, it's not super necessary for you to do when you're coding. And then these as well, just making it shorter so I don't have to type out math.factorial every time, and instead I can just write factorial or pi. Just some nice little tricks that you might want to try out. So to define a cosine function, I made a function. So first we start with our def term, then the name of our function, approx cos n terms, and then our inputs x and n. Now we're going to start with y is equal to 0. This is because we need y to exist in order to add values to it. And then what we'll do is we'll make a for loop. And then in this for loop, we basically say for however many n terms, let's say there's 5, it'll go through 5 times. We're going to create a term and then add it to y. So what this term is, we're actually going to break it down a little bit. So -1 to the k, this is how we get that negative and positive alternating sign, which we see back here by saying that, when -1 to the 1, that's going to be a negative number, but when -1 is 2 or 4 or any even number, it's going to be positive. And that's how we get that alternating thing. So that's how we get that. Then we have x to the 2k and factorial of 2k. And both those things make sure that those numbers are not only even, but the same number here will be the same number here for any k, which is exactly what we see here, which is great. So, and then we return y. So once we have made our function, we can actually make an x range. I just chose to do -2 pi to 2 pi because it's a cosine function. And then we're going to get our y values from this function we built using x that we just made. And then let's just say 8 terms. And then we're going to simply plot it by just using matplotlib as plt.plot of x and y. And we run this code. We can see here, we kind of have an approximation. We can definitely tell that this isn't a perfect cosine curve, but it is something like that. So let's keep going. Now let's say that we want to approximate and see how accurate we need to be in order to get a good approximation of a cosine curve. A great way to do this is by making subplots. Subplots allow you to compare data directly next to each other because it will be anywhere from 2 or more figures in the same image. So here what I do is I actually create a new x basically space by using numpy.linspace. This is a great tool to use. It's again a lot like range where you put a start value and an end value and then how many steps you want. So here we're going to do 600 steps, so that way we have a lot of steps. Then we're going to get our values from the function before doing something called a list comprehension. A list comprehension is just a fancy way of putting a for loop in brackets, basically, because what it says is for value in x, we're going to take that value of x, put it into this function with 7 terms here and 55 terms here. And we'll get back those values and be able to plot them. So here in subplots, first you have to define how many figures you're doing. Here we're just doing 2, so that's the number I put. And then this is the whole image size. Then fig.subtitle is how you make a title. And then something really cool is that subplots actually has a really cool way of indexing. So because I put 2 here, Axes already knows that for when I index it to 0, that will be the first plot. And when I index it to 1, that will be the second plot. So as you can see here, for x of 0, we're going to plot x and y1. And then for x of 1, we're going to plot x and y2. And then we set those titles. And this is just a fancy way of making a nice layout. And then we say plt.show, that's the most important part. It actually makes the image appear. And here we can see what this outputs. And here, this is a great way to analyze it, right? We can clearly see by adding more terms, we get a better cosine approximation, which is great. That's what we expected to see and is a great way of learning how Taylor series work. So let's say now, okay, we understand that, but let's really make sure, right? Let's look at 5 terms, 8 terms, 13, and even 20 terms. Can we do those all in the same plot? We can. So here we're going to do 2 figures and then another 2 figures. This is going to create a 4x4, like 1 figure in each square. You'll see how it looks in a sec. Then we have figure size, which again is just the size of the overall image. These are some parameters I'm not really going to talk about, but they're not super duper important, and you can look more up on your own into that if you would like, or come talk to me about it. I'd be happy to talk more about it. Again, we make a title, and then this is the cool customization, which is font size. You can add that in any label or anything, and it's cool because You can make it how big or small as you want, customize your things. They have a lot of cool customizations in Matplotlib, so I definitely recommend looking more into those. And then what we do here is we use a really cool function called enumerate. You'll probably see this a lot if you code with AI or just in general. Enumerate is awesome because it makes an index. That's what the I is going to be. And then n is the actual value for n terms. So for example, in n terms, we have 4 values, 5, 8, 13, and 20. So for the first time it goes through this list, I will be 0 because that's the index, and n will be 5. Then for the second time, the index will be 1, and n will be 8, and so on and so on. So anyways, in this loop, it's going to make a row and a column. The row and a column, this is a fancy function to basically say, it's to create the indexing of what a row and a column is and like where we want them. I wouldn't worry too much about understanding more about that. But then again, we get our functions from the same list comprehension we did before, and then we start to plot. Again, this uses the same comprehension we were using before, which is super cool. We have row and column for each of these, and then within our axes, and then we plot X and Y. We put a nice label in there. And then we also here are plotting X and actually NumPy's cosine function. I'm making it a dashed line that is light gray so we can really see the difference between our approximation and an actual cosine function. Then we set a title, put on the legend, turn on the grid, and then we set Y limits just so the figures are a little clearer. This also just sets more labels. And then again, type layout and show. So when we run this code, this is our result. And as you can see, the more terms we have, the cosine approximation does get much more accurate. Especially compared when we look at this 5 terms to this 20 terms, right? It looks a lot better. So again, subplots are super helpful because otherwise they would have to be in 4 separate things. And it might be hard to tell what the difference is if they're not right next to each other. And it might be even harder to tell if you don't have this gray line here, right, to tell you the true values. So it's a very useful thing. The next thing we're going to talk about is also very helpful. It's data fitting. Very similar concept. It's except we're going to use a different module for it. We're going to use SciPy. SciPy has a lot of cool things for data analysis. One of this is data fitting. So we're going to use their curve fit function. This is a way to specifically import a specific function. It would be just as valid to say import SciPy and then do scipy.optimize.curvefit and then parentheses of what you want to do your curve fit for. Again, it's just a thing where like you're trying to leave a little more room for other things in your code to make it more readable. So this part isn't super important. This is just so I can generate some random data so that we can see if our model will work. But then what we do in order for this function to work is we need to define a model. So what do we think this curve is going to approximately look like? Here, we know that it's going to be a cosine model. And that's because what I'm creating here, as you can see, is based off of a cosine curve. So we're going to read in 4 parameters, x, a, b, and c, and then we're going to return a cosine function with modified parameters. And I'm sure you've seen in past classes as well how those specific terms modify each thing of the cosine function. And that's exactly what we want because we want to make sure that even if our cosine model isn't like an exact curve, that our model can be representative more of the data than like an idealized curve, if that makes sense. So then the next thing that's really important for SciPy is you're going to need an initial guess. So an initial guess is just what you think these values of A, B, and C are going to be. Here, what we use is this is basically a clever way of calculating the median height of the Y data, because that'll approximately be like where the amplitude should be. So that's your A. Then B and C, we've kind of done just based off of like the true values. Obviously, when you don't know the true values, it sometimes takes a little bit more, but obviously, we're not always going to be modeling something as complicated as a cosine curve. So do with that what you will. But then what you can do is curve fit returns two values. People often call these popped and pcove. And then you call your function. So curve fit, like we imported from above. And then we put our model in, our x data, and our y data, which is what we generated above. And then these are our initial guesses. And from there, these are fancy these ones are fancy F strings of just, we're going to print out what the best fit parameters are. That's what SciPy returns. And then SciPy also returns our actual model. So we want to look at this, obviously. So what we're going to do is we're going to use plt.scatter. We're going to plot the x data, the y data, put a label on it and a color. And then we're going to make an x so that we can go through this whole thing. And then we will plot the cosine model as well from SciPy so that we can see how this fitted function if it actually fits our data. So what they did here is they took in this x and then also this popped, which is from this curve fit. And that's how we get that curve, because it's going to basically give the correct guesses or best fit parameters into the model and return it. So again, put some labels, title, legend, and show. Let's see how it looks. And we can see here, this fitted function fits the data pretty well. Not a lot falls off the curve, and it kind of goes along that trend. So, and we also get the best fit parameters up here. So this is really useful. Again, if you were just looking at this without this curve, I can just comment this out. And you can see a little bit of a pattern here, right? Like that makes sense, but doesn't it seem so much clearer just by adding in that line? So again, data fitting is super important. It makes things a lot easier to see. And yeah, that's what I have for you today. The rest of the slides that I have on there are basically a summary of what we went through in this notebook, so I'm not really going to talk about it. If you have any questions, please feel free to ask me or Tim. I would love to talk more about this. But yeah, thanks for listening. I hope you have a great day, and we'll see you in class.